Let's welcome Aleksandr Kazachkov from University of Florida. He is going to talk about strengthening the polyhedral disjunctive cuts. Please go ahead.
Thank you so much for that introduction and for the invitation. It really is an honor to be presenting at the MIP workshop. As the last speaker, though, before I go on to my talk, I'd actually like to take a moment to thank Timo, Yuri, Robert, Carla, and Juan for the really wonderful job that they've done organizing now 2 online editions of the MIP workshop. So if the whole audience could just join me in thanking them over chat and sending their appreciation, I think it would be very well received while I start my talk. So thank you very much. Okay, so yes, I'll be talking about strengthening V polyhedral disjunctive cuts. And this is based on a continuation of work that I started during my PhD with Egon Balish. Egon would have been very pleased that I'm presenting our joint work here at the MIP workshop, and he was a big fan of it. I don't know if I can quite meet the, let's say, enthusiasm and vivaciousness that he had in his talks, especially in this online format, but I will try to do my best. So the question that drives my methodological research is, how can we make stronger disjunctive cuts practical? And here by stronger, I mean stronger than cuts that already exist in optimization solvers and are deployed by them. And practical, I define success as if we take these stronger cuts and make them available to users. And then actually, I would like to have great success, which is if by default, some general disjunctive cut strategy would be enabled in these solvers. Already, we know that cutting planes are a critical component of optimization solvers, and it was one of the driving forces for modern integer programming software to go from the pre-90s era to what we see now and how we can just nip things. However, the cutting planes that helped drive the success are coming from a relatively simple family. Most of them can be expressed as split cuts. On the other hand, there are many stronger cuts that exist in the literature, and here just is a partial list of co-authors that have done mainly computational work on this question in the past decade. I probably should have just taken a participants list from the workshop, but here are a few of the papers that I used and built upon in my work. So yes, these theoretically strong cuts do exist, but I think it's fair to say that none of them have really entered into the optimization solvers for a variety of reasons that I don't have time to go into in this talk, but we'll be happy to talk about my opinions offline. However, I do want to express some optimism, some selfish optimism maybe, which is that the framework that Egon and I were developing during my PhD called the V Polyhedral Framework, it does show some promise for being able to generate stronger cuts more efficiently than existing or than previous methods from large multi-term disjunctions. So what I'll do now is I'll go very quickly over what the V Polyhedral Framework is and some results, and then I will actually go into the more recent work that I've been doing, still based on my dissertation on strengthening these cuts. A little bit of primer and warm up for you. We're optimizing over a rational polyhedron, and what we'd really like is to get the integer points inside of there. But because that is hard computationally, instead we relax those integrality restrictions and we solve something over the linear programming relaxation feasible region, which we denote by P. And let's say X bar will be our point that we get for the LP relaxation. And now that point won't be satisfying the integrality constraints. So what we'd like to do is add another linear constraint that's easy to handle and gets us closer to the integer feasible region. How do we get these cuts? As Amitabh has already talked about, most cuts can be thought of as being derived from disjunctions. This is splitting the feasible, or splitting Rn, let's say, into a bunch of sets, the union of which cover all integer feasible points. And so when you do this, you're left with a few, let's say, parts that I'm going to call disjunctive terms, and I will be denoting them as P superscript T. And here, this is the so-called H polyhedral description, which is the hyperplanar inequality description of a polyhedron. Now, every single polyhedron, here I'm taking just one of those terms, has another equivalent way of expressing it, which is in terms of its extreme points and extreme rays. By the way, I'm going to assume that these are pointed polyhedra, so they do have vertices. So, but that's not necessary for the theory, that's just for the purposes of this talk. So here is in green the two vertices and extreme rays of this polyhedral or disjunctive term. And V polyhedral cuts start with the premise that if a cut is valid, well, a cut is valid for that term if and only if it's satisfied by all of those points and rays. So what we can do is we can put those points and rays, the vertices and rays, into a linear program for each term where the variables are now alpha and beta, and try to get inequalities. And now the nice thing about this compared to other methods is that the variables being alpha and beta mean that it's only of dimension around the same as the ambient space in which P lives. And this is called the V Polyhedral method because this is the V Polyhedral description that Jamie had already introduced the V Polyhedral terminology earlier in her talk. Okay, so what we do is we build a linear program, which I'm going to call the point rate linear program because it's constructed with constraints of points and rays, and I'll call it the PRLP. The key thing with this, I mean, there are many questions I don't have time to discuss in terms of making this work, but the key thing I'll talk about right now is which points and rays to use. What's known is that the set of extreme points and extreme rays for a description of a polyhedron might be exponentially larger than the number of inequalities that you need to describe. So that set of vertices and rays that I had before, if we use that at the points and rays, that's far too large for us to use in practice. Prior work has attempted the same type of PRLP, and what they've done is used row generation methods to generate cut, check if it's valid, if not, add more constraints and iterate in this way. However, that's been shown to be relatively expensive. So what we're going to try to do is generate a set of points and rays that for every feasible solution to the PRLP, we're guaranteed that it's a valid cut. I won't go into all of the details about it. I'll just show a picture for a simple split disjunction on a variable, but note that the same exact method would apply for general disjunctions. And what we do here is, let's say we take a split disjunction, we're left with two disjunctive terms. The key thing that we would like is actually to form a V polyhedral relaxation of each of those disjunctive terms. What that means is that the convex hull of the points plus the convex hull of the rays is a relaxation of P1 and P2. And we actually use one of the simplest ones that you could think of. We optimize over each one of those disjunctive terms. And then on each one of those points, there will be n linearly independent inequalities, which define a basis cone. And that's what we use. The polar of that has 1 point and n rays, where n again is the dimension of the ambient space of P. And that's a very compact description because now we put n+1 constraints per disjunctive term and multiplied by the number of terms, we have a relatively small LP to solve to get cuts. And we know they're valid because that's a relaxation of each disjunctive term. So cuts valid for those are therefore immediately valid for the disjunctive hull. Okay, so I'm putting a check mark here, even though I haven't really convinced you very much, but in the interest of time to move on to the second half of the talk, I will just say that we do have this promise that, not this promise, but this promising method in this way that we can efficiently and non-recursively generate strong cuts with this framework. By efficiently, I mean compared to the method of lift and project cuts, in which we need to formulate an extended formulation or a higher dimensional formulation in order to get cuts. And non-recursively, because typically in what's done in practice is you apply cuts in rounds and you resolve the LP. And there could be numerical issues that arise as you proceed in this iterative fashion. So what we prefer is to maybe solve a few more LPs to get stronger cuts in the beginning, but not generate cuts based on other cuts if we can avoid it. So that allows us to get stronger cuts by generating larger disjunctions, taking advantage of this efficiency. And we also do have theoretical results that even with the simple PRLP or the simple V polyhedral cuts, we can get facet defining inequalities for the real disjunctive hull under certain conditions. Okay, so many of you have seen some of these results before, so I will talk about it quite briefly about what we tested with the simple PRLP or the simple V polyhedral cuts. These cuts are implemented in CoinOR, which is an open source framework and actually available on my Git. For the results I'm showing, I will only talk about the percent gap closed on a set of instances in which we know the IP optimal value, and we're trying to get from the LP optimal value to the IP optimal value, and higher is therefore better by closing that gap. And at least initially, I'm going to show you results compared to Gomer mixed integer cuts, which is a pretty reasonable baseline because we know they work well in practice too. I selected several instances that are under, let's say, 5,000 variables and 5,000 rows. So not super small, but not very large, just because I'm doing many experiments from MIPLib, NEOS, Coral, and those sets. And actually, I think the key thing here is that we're testing quite large disjunctions. We're using a partial branch and bound tree that's generated for each of those instances. And we stop when there's up to 64 terms. And that's much larger than, for example, split disjunctions, which just have 2 terms. OK, so here are the results for these initial experiments. And the first thing to say is that the y-axis is percent gap close. So again, higher is better. And Gomer cuts close for these instances about 16.6% of the gap. And V Polyhedral cuts close about 14% of the gap. So you're saying, OK, well, it seems like they're not doing very well, Alex. Why did you even present this work? This particular difference between the V Polyhedral cuts and the Gomer cuts, Egon had a hypothesis, and that's what's going to be talked about or driving the second half of this work, which is that Gomer cuts are strengthened intersection cuts, basically. You apply monoidal strengthening or some other modularization of coefficient procedure to go from the initial cut to a stronger cut. V Polyhedral cuts do not have that same method applied to them, and there's a small barrier that needs to be overcome before something like that can be tried. So at least that was Egon's hypothesis, and I believed it, and I started working on that process in order to see if it can be resolved, this difference between those two cuts. But anyway, actually, even without that, it doesn't really make sense to look at either of those cut families on their own, because in practice, we would use both of them together. And what's interesting is that when you apply both of these cuts together, you have a dramatic improvement in the gap closed. So it seems at least that those cuts are doing things in different parts of the region. I also tested these cuts in Groby as user cuts. And what I saw is that a kind of a similar story at the root node after the first round of cuts, the V Polyhedral cuts are still helping in addition to the cuts that Groby uses. And this continues to help even after Groby applies many rounds of cuts, which even though we don't apply these cuts recursively, we just do one round. Even after Groby does cuts on cuts, at the end, V Polyhedral cuts still help by quite a bit compared to the existing cuts. Now, to build on the point that these cuts are doing different things, I also looked at instances in which V Polyhedral cuts seem to do well. And on those instances, actually, V Polyhedral cuts on their own close over double the gap that Gomer cuts close on their own. And this continues also for the Groby cuts as well. So kind of to conclude this part, V Polyhedral cuts seem to be doing something different than what existing cuts are doing. Then I did test these cuts in branch and bound, and I saw some hope, but also some challenges. Mainly, if I knew which disjunction to use for each instance, I could get quite a bit of a speed up for the time to solve with Groby. But I haven't really accounted for variability. Nevertheless, I did check, and there are instances in which, regardless of variability, VPCs consistently help compared to the baseline. So I would say that there's an opportunity, I think, for us as researchers to see what we can do computationally for stronger cuts that's special, because I think they are doing something different than what all the cuts that we've been working with before are doing. But also that there's that mystery of, can we close the gap between V Polyhedral cuts and Gomer cuts based on, let's say, modularization of the coefficients. All right, and so towards that, given that I would like to strengthen cuts, I actually first am going to start with trying to build a correspondence between V Polyhedral cuts and lift and project cuts. So going back, here's another polyhedron, and we're optimizing, and we get some solution X bar. And maybe we impose a disjunction that gives us these disjunctive terms. And in whatever procedure we get a cut. Well, one of the ways to get this is through the lift and project method. And that really corresponds to solving a system where you have these constraints on the right, and in particular, you have these extended, this higher dimensional space includes these VT variables, which are multipliers on the constraints that certify the validity of the cut. This is what that looks like. Essentially, it's showing that the normal to the cut lies in some normal cone on each of the disjunctive terms. And what I would like to ask is whether we can find those multipliers without ever explicitly solving a higher dimensional linear program. The motivation, again, is to strengthen disjunctive cuts. And here's why. If we're given a specific cut, let's say alpha x greater than or equal to beta bar, and a disjunction where here I've broken up the inequalities describing that disjunctive term into the constraints from P, which subsume also the variable bounds, and the inequalities, additional inequalities defining the disjunction, dtx greater than or equal to dt0. Well, then we can actually strengthen coefficients of those cuts using the formula below, using a monoid M and a lower bound L for each of those inequalities dtx that is valid for all x and p. But also we need those multipliers that we don't have when we solve things using the V Polyhedral Framework. And particularly we need the UT0s, which are the multipliers on dtx greater than or equal to dt0. And we need the UTK, which is the multiplier on xk greater than or equal to 0 on that particular constraint. So we can do this kind of strengthening, but not yet, not until we get those multipliers. Well, one way to do it would be basically now we have this alpha bar and this beta bar, and we can solve the linear system in order to get the VTs. But I don't really want to do that because that seems quite expensive. So I was wondering if there is anything that we can say, at least for the particular case of the V Polyhedral cuts generated through that simple relaxation through the cones, that's better than that. So recall that for the simple V Polyhedral cuts, what we're doing is we're doing a cone on each disjunctive term that consists of just one point and n rays, so it's a simple cone. And because it's this simple cone, the corresponding set of constraints is actually invertible. In fact, that inverse is available to us when we're computing cuts as the basis inverse. So this is quite nice because then in order to compute cuts, we can really just multiply the cuts against this basis inverse and get those multipliers. Moreover, for the general case, it's a little bit less efficient, but it can still be done somewhat efficiently by getting bases and computing almost the equivalent type of process to compute those multipliers for every single cut rather than solving a large linear system to get coefficients for each cut. So basically, at least it seems somewhat hopeful that we would be able to avoid a more expensive CGLP-based method, still work in a lower dimensional space to generate cuts, and we would be able to get multipliers certifying that validity, which I think actually even aside from strengthening would be independently useful for some people. So I do have code that's that does this with pretty good efficiency, and I've also been checking it quite carefully for accuracy, validity. And I'd like to present a few, I would say still preliminary results with this code. We again test VPCs generated with disjunctions with up to 64 terms. And for this particular code, because I was trying to really make sure that everything was valid, I'm actually using the eigen library to solve a subset of the linear system. We still have the constraints, those n constraints defining the cone for each disjunctive term. And we actually have the basis for that too. And we just solve that linear system using eigen, not using the inverse trick at this point. But I have both of those kind of implemented and I'm testing them against one another. For the strengthening for two-term disjunctions, I use kind of a closed form test of the M1 and M2 for the monoid. I use 0 plus minus 1 minus 1 plus 1 and so on for just the first and plus 1 minus 2, plus minus 2 and minus plus 2. And now for strengthening with more terms, you have to solve a little bit of an optimization problem. There might be a better way to do it, but at this point, what I'm just solving is a very small MIP. You know, we just MIP it these days. And this is a MIP with just the number of terms of the disjunction, integer variables. However, those are general integer variables, so they could in general lead to a hard problem even with this few terms. But at least for now, I haven't run into many computational efficiency issues testing this. All right, so let's see what the percent gap closed looks like. Here I'm showing for a two-term disjunction at first. So what that means is for Gomery cuts, this is for every single fractional variable, which leads to a split. It's generating one cut and then strengthening it. And that gets 16.6% gap closed. Meanwhile, for VPCs, it's just a single fractional variable, a single split disjunction, but we're generating possibly many cuts from that split disjunction. So it's not really unexpected that on their own, these cuts are going to be much worse than Gomer cuts because we're not really taking any diversity into account across different fractional variables. But what the interesting to me is how does strengthening perform on these instances for this type of disjunction? And what we see is that strengthening actually causes, it leads to about 150% improvement in gap closed over unstrengthened cuts on these instances. So that's a partial kind of hopeful answer to Egon's hypothesis that maybe this does explain the difference between V polyhedral cuts on their own and Gomer cuts on their own. And here's an instance example. For those of you who are computational, you all probably have a favorite instance of yours. So some of you might have this as your favorite instance. It's actually not my favorite, but it's pretty good. And you might recognize just by the LP value, which is 917, and the IP optimal value, which is 924, what that instance is. But if not, it doesn't really matter. I would just really like to highlight, this is, by the way, a screenshot of the log of my code output. I'd like to highlight these lines. So again, 917 is the optimal value of the LP, and unstrengthened VPCs close 0% of the gap. But after strengthening, just like Gomer cuts, 100% of the gap is closed. And this instance is 10 teams, by the way, which we also saw in Elias's talk. So this is really like also another, at least on one instance, supporting that same hypothesis. However, there's a little bit of maybe a negative news that when we go to larger term disjunctions, so here, for example, this is for 4-term disjunctions, again, still one disjunction per instance, the amount of gap that's closed, extra amount of gap that's closed via strengthening is relatively small. It's only another 0.5%. With 64-term disjunctions, we're only closing 0.1% more of the gap via strengthening. I do want to point out that if we took the best result on an instance by instance case across the 2-term, 4-term, 8-term, 16-term, 32-term, and 64-term disjunctions, the strengthening actually pushes us past the Gomer cuts even on their own. But as I mentioned before, that's not super relevant in the sense that we are going to be using those two cut families together anyway. But I did want to point that out. But I also want to kind of form a hypothesis of what's explaining this, what's a negative improvement as the terms get larger. Let's work with an example. Here's a 4-term disjunction and a cut that I would really like to strengthen. Here are the two disjunctive terms that I then have my cone relaxation for. And in blue, I'm showing the normal cone, and also the fact that the cut lies inside of the normal to that cut lies in the normal cone and can also be used to define the multipliers that certify that cut. Now, going back to the strengthening formula, which is shown here, what we really need is these multiplier, this multiplier UT k, that is the multiplier on the xk greater than equal to 0. And if that multiplier is 0 for all of the terms, then this is not going to lead to any meaningful strengthening, at least that I know of. I mean, maybe there's a different way to work at it, but it doesn't seem to work. And for sure, like if you look at the formula in the monoid, it won't work that way. But yeah, and by the way, in this particular case, you'll see that it's not very hard to see. It's not very easy to see where the bounds are, but the bound over here would be on x bar greater than equal to, less than or equal to 1, x2 less than or equal to 1, and there are actually no lower bounds over here. So we don't have any bounds being multiplied with a positive multiplier. But there exists a different set of multipliers for relaxation of your disjunctive term, in which the multiplier on the upper bound on x2 can be used to certify the cut and has a non-zero value. This is something that has already been observed in Balish and Koalitsa from 2012, that sometimes weakening a disjunction can help the strengthening. And this is exactly what I think is happening in these larger disjunctions. We're not getting any bounds that we can strengthen on, and therefore we're not seeing much strengthening. This is just a hypothesis. I don't have any confirmation from it, and I don't yet know how to act on this knowledge, but that's kind of where I'm going from here. So to wrap up, I am optimistic about the V Polyhedral Framework. I think it mitigates some practical challenges that other stronger cutting plane methods have encountered. It's not ideal, it's still expensive in many cases, so I think it wouldn't be the kind of thing that you would use for every single instance, but there are times when you would want to do it. And yes, it has one thing, that it's better computational efficiency than compared to, let's say, lifting project cuts. And they are much stronger than existing cuts and different than existing cuts in solver. The strengthening experiments, I think they show promise, but also some challenges to applying these coefficient modularization. Particularly, can we find better multipliers efficiently? And also optimizing over those monoids should be done, ideally not with a small MIP, but something a little bit more intelligent, perhaps a heuristic, because we don't really need the best strengthening coefficients, but a good one would already suffice. Finally, let me close with an ad to use my work. If you have a family of instances or problems in which you would like to test stronger cuts, let's apply my V polyhedral cuts and see what they do. If you have an instance in which you think you have a special disjunction that you would like to use, then my cuts might actually work even better for that case. Or perhaps you have a disjunction of your own and a cut that you've generated, but you really need a certificate. So I can actually provide you that certificate and maybe even strengthen those cuts using that certificate. So if you're interested in talking about it with me, please come see me anytime or talk to me on Slack. Thank you for your attention, and I'll take any questions now.
Thanks, Aleksandr. Thanks for the wonderful talk. Now let's take the time to answer some questions. Please type your questions in the Q&A or just unmute yourself. So we first have a question from Akshay, maybe around page 23 on the computational results. Akshay asks, do you use the same standard normalizations as for CGLP, and do they have similar properties for PRLP?
So no, I use actually beta equals 1 normalization for this, because I am working in the non-basic space in which the origin is corresponding to X bar, the LP solution. And so all cuts, all inequalities that cut away X bar have a right-hand side of 1. So I'm not generating inequalities that don't cut away X bar, but I also have some efficient, let's say, tricks in terms of how I work with those. So it's a subset of the possible cuts, but it doesn't face some of the same issues that the normalizations that we use in for the CGLP have. So yeah, basically it's this particular normalization working in a particular space that seems to work well so far.